for today's lesson, we will be discussing about the logarithmic differentiation. So we will discuss how or when do we use this logarithmic differentiation in identifying derivatives of specific functions. So before we proceed with the process or the step on how to identify when to use our logarithmic differentiation, so let's analyze this one first. So if you will look at this given function, y equals x raised to 2x plus 3, and then you're asked to get the derivative of this function, you might think of using the chain rule or use the power rule, okay? But using those techniques is wrong or incorrect, because let's say you will use the chain rule, so that means your u here will be the 2x plus 3, and then you will change it to x raised to u. So this one, we cannot use here the power rule since our exponent is u, and we cannot use also the derivative for exponential function because the base here is a variable as well. So we cannot use those techniques. And if that is the case, that is when logarithmic differentiation becomes handy. Now, what is logarithmic differentiation? It is the method of differentiating functions by taking or by first taking logarithms and then differentiating or getting the derivatives of our function. So how do we do logarithmic differentiation? So you can just simply get first the logarithms of our function, and then after you get the logarithms, you have to differentiate. So this process or method is what we call as logarithmic differentiation. So this approach allows calculating derivatives of power, rational, and some irrational functions in an efficient manner. So when are we going to use logarithmic differentiation? So we can use this if we notice that our function or the given function is too complicated, if we will be using the product rule, the quotient rule, and something like that, or if we notice that we cannot apply the different rules that we know about derivatives. So this is when we can use the logarithmic differentiation. So in order for us to do logarithmic differentiation, let's say you have y equals f of x. All you have to do is just to take the natural logarithms of both sides. So what does it mean? So you just have to multiply ln on both sides of our equation. So it's like we are getting the natural logarithms of both sides of our equation. And then from here, you just have to simplify. And in simplifying, you have to apply the different rules that we know about logarithms. And then you get now the derivative. Now, one thing that we have to remember is here, since it involves natural logarithms, though it's applicable for the other types of logarithms as well, but we will be focusing with ln only for this one. You have to remember the derivative of ln. So last time, we discussed the derivative of ln of x is 1 over x. But, of course, in this case, there are times wherein it's not equal to x only. So let's say ln of x plus 5, ln of x squared. So we have to use the chain rule. So to make it short, so the derivative of ln of u can be expressed as a du over u, or the derivative of u over u. So in simplifying, we have to take note of the properties of natural logarithms or the logarithms in general. So the first three here, so ln of 1, that is just equal to 0. ln of e is equal to 1. And then we have ln of e raised to x is equal to x. Then this 3 right here, these are the most commonly used properties whenever we simplify. So let's say we have ln of y raised to x. So if your argument is raised to any exponent, all you have to do is just to put it in front. So you can just put it in front, then multiply it with ln of y. So that's it. Example, ln of x plus 3 squared. So let's say this is our function. So if our argument x plus 3 is raised to 2, you just have to put it in front and multiply it with ln. So this can be written as 2 ln of x plus 3. Okay? And then for the fifth property, so if our argument is multiplied, so we can just simply separate the two terms using addition. Example, ln of 3x squared. So 3 is multiplied. You can just think of it as 3 is being multiplied to x squared. So just to give you an example. So it will be ln of 3 plus ln of x squared. So something like that. So you can write them separately. And if the argument is divided or separated by division, you can still separate them but with subtraction. So example, ln of 4x over sine x. So you can write this as ln of 4x minus ln of sine x. So these are just some of the properties that we can use when we simplify our logarithms. So let's try it with this example. Let's get the derivative of y equals tangent of x times x minus 1 raised to 5 all over 4x squared plus 1 squared. So if you will look at this function, you can see that we have the numerator, we have the denominator. So we can actually use the quotient rule here, but if you will look at the numerator, we still have to use there the product rule. And for the denominator, if we're getting the derivative of our denominator, we still have to use the chain rule. So it requires a lot of task in order for us to get the derivative of this using the derivative rules that we know. So let's try to use the logarithmic differentiation. So first is we have to get the logarithms of each side by multiplying ln. So we have here ln of y is equal to ln of, and then just put parentheses, tangent of x times x minus 1 raised to 5 all over 4x squared plus 1 squared. Okay, so once you already done getting the derivatives, we now have to simplify this. So this is where we will apply the properties that we know. So for ln of y, it's just ln of y equals, here since we have a fraction, we can separate this, the numerator denominator, into two using subtraction. So we have ln of tangent of x times x minus 1 raised to 5 minus ln of 4x squared plus 1 squared. Now after that, you can check again the terms that you have, and looking at this, we can still write them separately using addition because the terms that we have here are being multiplied together. So we have ln of y is equal to ln of, then we have tangent of x plus ln of x minus 1 raised to 5, then just connect this one, minus ln of 4x squared plus 1 squared. So you just have to make sure first that everything is simplified or everything is expanded properly. So we have ln of y, we have this one, but here we can still see an exponent 5 and 2 from our argument. So that means we can still put that in front of our logarithm. So we have ln of y is equal to ln of tangent of x plus 5 ln of x minus 1 minus 2 ln of 4x squared plus 1. So there you go. Now after simplifying, we now have to get the derivatives of both sides. Now notice here, we need to get the derivative of ln of y. So get the derivative of ln of y. But since this is a y term, that means we have to apply implicit differentiation. Remember, whenever we get a derivative of a y term, so we multiply it with dy over dx. So the derivative of ln of y is 1 over y, but we still have to attach dy over dx to it. But remember, dy over dx is just the same as y prime. So we can just simply write this as y prime over y. Okay, so that will be the derivative of our ln of y. So how did that happen? We apply implicit differentiation. So here we have y prime over y is equal to, then let's get the derivative of each term. So first, ln of tangent of x. So a while ago, I told you that to get the derivative of ln of u when the argument of our natural logarithm is not equal to x, so all we have to do is get du over u, or the derivative of u all over u. So the u here is the tangent of x, so this is u. So that goes to the denominator, tangent of x. And for du, just get the derivative of tangent of x. So what's the derivative of tangent of x? That's secant squared x. So that is the derivative of our ln of tan x. Next, for this one, so we know 5 is multiplied to ln of x minus 1. But since this is just a constant or a number only, so we can just write here 5. And then multiply it to the derivative of ln of x minus 1. So again, we have here ln of u, wherein the u is x minus 1. And then its derivative is 1. So there. Minus. And then do the same thing for this. You have 2 times. This is ln of u. Our u is 4x plus 1, or 4x squared plus 1. And then the derivative of 4x squared plus 1 is 8x. So there. So we're now done getting the derivatives. After that, we just have to simplify. So just multiply everything that you need to multiply. So let's just write here y prime over y is equal to secant squared x over tangent x plus, and then we have 5 over x minus 1. So just multiply this, and then the 2 and 8. Minus 16x over 4x squared plus 1. So let's just write here y prime over y is equal to secant squared x over tangent of x plus 5 over x minus 1 minus 16x over 4x squared plus 1. Okay, so this is the function that we have now. So on this side, we only need the y prime. So we don't need the y here because, again, we're just solving for the derivative. So in order to remove y, all we have to do is just to multiply both sides by y, so that this will be cancelled. If that is already cancelled, we can just write y prime is equal to, and then y is multiplied to this function. So we can write y times this whole function, secant squared x over tangent of x plus 5 over x minus 1 minus 16x over 4x squared plus 1. Okay, so last step that we have to do, since this is already the derivative, y prime is equal to, and there is still a variable y here, so we have to remove this variable. So if we will go back to our function, we know that y is equal to this function right here. So what we can do is we can just simply substitute that function into y, and that will be our final answer already. So that is tangent of x minus 1 raised to 5 all over 4x squared plus 1 squared. And then times, then you connect this one, secant squared x over tangent of x plus 5 over x minus 1 minus 16x over 4x squared plus 1. And then that's it. That is now the derivative of our function. For our next example, y equals x squared plus 1 raised to sine of x. So let's get the natural logarithm of both sides. So ln of y is equal to ln of x squared plus 1 sine x. So after that, of course, we have to simplify. So this is just ln of y is equal to, now this one, we have the exponent sine of x, and based on the property, we can just simply put it in front and multiply it to our ln. So we can write here sine of x ln of x squared plus 1. So remember, sine of x is multiplied to ln of x squared plus 1. So nothing can still be simplified here. So let's proceed with derivatives. So we will now be getting the derivatives of each. So get the derivative of ln of y, and then get the derivative of sine x ln of x squared plus 1. So for ln of y, its derivative is y prime over y using implicit differentiation. And then from here, since these two are being multiplied together, we can, or we have to use our product rule. So this is u and then this is a v. So let's get a derivative using the product rule. So u times the derivative of v. So our v is ln of x squared plus 1. So this is in the form of ln of u. So u is x squared plus 1. That goes to the denominator. And then the derivative of x squared plus 1 is 2x. So there, that's the derivative of v plus v du. v du times derivative of u. Derivative of sine x is cosine of x. So there. And then, let's just simplify this. Y prime over y is equal to, then multiply. So we can just write here 2x sine of x over x squared plus 1. And then this one, just write it as cosine of x ln of x squared plus 1. And since we're done simplifying, we now have to multiply both sides by y so that we can cancel it. So this will be cancelled. So we now have y prime is equal to y times the 2x sine of x all over x squared plus 1 plus cosine of x ln of x squared plus 1. Okay? And then we just have to write our y, or substitute the value of y, which is our function, x squared plus 1 raised to sine of x. So we have y prime is equal to x squared plus 1 raised to sine of x times 2x sine of x over x squared plus 1 plus the cosine of x times ln of x squared plus 1. And then that will be our final answer. So that is now the derivative of our function. And for our last example, y is equal to square root of x raised to square root of x. Okay, so let's use again the logarithmic differentiation here. Ln of y is equal to ln of square root of x raised to square root of x. Since our argument has an exponent, so we have to multiply it in front. So ln of y is equal to square root of x times ln of square root of x. And then let's get the derivatives. So get the derivative of ln of y and also the derivative of square root of x ln square root of x. Now here, this one is y prime over y. This one, as you can see, we have two terms that are being multiplied together. So this is our u, this is our v. That means we have to use our product rule. So let's use the product rule. U dv times the derivative of v. Our v is ln of square root of x. So that is ln of u. Our u is the square root of x. And then derivative of square root of x. So as what we know, the derivative of square root of x is equal to 1 over 2 square root of x. So just transform it first into exponential form. So we have x raised to 1/2 and then apply the power rule. You will arrive at this answer. So that is 1 over 2 square root of x plus u dv plus v du. Derivative of u, again, derivative of square root of x is 1 over 2 square root of x. And we just have to simplify this. So we have y prime over y is equal to, here, you can cancel out the square root of x because they are multiplied together. So you will be left with 1 over 2 square root of x. Plus, and then you can just simply multiply this, ln of square root of x over 2 square root of x. Okay? If you want, you can write them as one fraction since they are just the same. They have the same denominator. So we can write this as, so here, y prime over y is equal to 1 plus ln of square root of x over 2 square root of x. So you can just write it as like that because they have the same denominator. So that means you can write them as one fraction. And then to cancel out the y, just multiply both sides by y. So this is cancelled. So we have y prime is equal to, and then we have the y times this one, 1 plus ln of square root of x over 2 square root of x. And then last step is just to substitute the value of y, which is square root of x raised to square root of x, and then multiplied it to 1 plus ln of square root of x over 2 square root of x. So that is our final answer. So there. So we're able to get the derivative of our function using logarithmic differentiation. So that's it for today. I hope you learned something about the logarithmic differentiation and how to use it and when to use it in getting the derivatives of function, and see you next time.